Everyone. Today we are looking at our fifth lesson of this unit. We are going to talk about independent and dependent events and sort of looking at the probabilities of multiple events happening at the same time. This is going to allow us to do more and more complex and important useful problems. So let's dive in. Think about this. In November of 2016, the U.S. saw the first case. I'm not sure if there was quintuplets that were boys for that, but it was the first case of a set of quintuplets that were all girls. So think about this, and we will come back to it later. If the parents were to have another child, would they be more likely to have a boy? They've had 5 girls, roughly 50-50 chance, of having a boy or a girl. But if you have 5 in a row, are you more likely to get a boy on the 6th one for things to start evening out, or is it still 50-50? We're going to answer that kind of question today. As I mentioned earlier, we're going to find the probability of multiple events happening at the same time. You can call these kind of things compound events. They're multiple events in a probability experiment. Compound events may or may not affect each other, and whether they do or not, we call them independent events or dependent events. Independent events occur when one event has no effect on the probability of another. So like they're independent of each other. So examples like this are flipping a coin. So I flip a coin, I pick the coin back up. That first flip will have nothing to do with the second flip. They're independent of each other. If I draw a card from a deck, if I put that card back, then that does not, if that first card had no effect on drawing a second card, because I put it back, there's still 52 cards in the deck. It turns out that the genders of babies in a family are independent events. Even though a family has 5 girls, there's still a 50-50 chance of getting a boy with their next baby. Those are independent events. We've already looked at how to find the probability of event A happening or event B happening, and we added probabilities. To find the probability of 2 events happening at the same time, so probability of A and B, we multiply probabilities together. And just want to add in here some notation that you may see in one resource or another. I'll just choose some red here. Another way to write this in terms of set notation is probability of A and this upside down U. That's another way to say the probability of A and B. It kind of is a formal symbol for intersection. So yeah, depending on the resource you're using or where you go to school maybe next year, you might see either notation. Just really quickly, in case you didn't catch it in the lesson before or it wasn't mentioned, another way that you may see the probability of A or B happening, you may see that written as probability of A and then this upside down U, B. U for union. So those are just different ways to say the same thing, but this multiplicative principle is really easy to use. You take the probability of A happening and you multiply by the probability of B happening. It's also an application. It's also called the fundamental counting principle. Sorry for that spelling error there. Let's do some examples. So let's do a really basic one right now. So in this example, we're flipping a coin and rolling a dice at the same time. So what's the probability of flipping heads and rolling a 5 in a single trial? So a coin in one hand, a dice in one hand. What's the probability of flipping heads and rolling a 5? So I might word it this way: for the probability of heads and rolling a 5. So using our fundamental counting principle or our multiplicative principle, we take the probability of flipping heads and we multiply by the probability of rolling a 5. Each of those things we already know. We looked at simple probabilities several days ago. Probability of flipping heads is a half. Probability of rolling a 5 is 1 out of 6. And that gives you a 1 out of 12 chance of getting a heads and a 5. So it's a really easy principle to use. Let's look at another example. So many of you guys have probably played the game of Yahtzee before. So in the game of Yahtzee, you roll 5 dice at the same time, and you try to make different patterns, like get all 5, which is called the Yahtzee, the same dice, or you try to get a straight or full house. We can actually now analyze the probability that just on your first try, you get a Yahtzee, all 5 dice matching. Let's begin. First thing to note here is that if you think of the first dice, it actually doesn't matter what the first dice is. So I'll say this: the first dice doesn't matter. Whatever that first one to come out and settle, because if the first dice is a 5, the other 4 just have to match it, and if the first dice is a 2, just the last 4 have to match it. So the probability of getting a Yahtzee, spelled that right, yeah, is the probability of getting the 4 matching dice. So after the first roll, the probability that the second dice matches it, well, there's going to be a 1 in 6 chance of getting a match. And for the third dice, a 1 in 6 chance of matching. For the fourth dice, there's a 1 in 6 chance of matching. And for the last one, 1 in 6. You may have already thought of an easier way to write that. Instead, if you didn't want to write the repeated multiplication, you could just use exponents. And that works out to 1 over 1,296. Or if you put that as a percentage, very rare, about 0.08%. So only once in every 1,296 rolls, you'd expect to get a Yahtzee on the first try. So as you can see, this idea of this multiplicative principle allows us to do much more complex problems. If you think back to maybe our first or second day, we might have had to draw a tree diagram, 3, 4, 5, 6, showing all the outcomes for each dice. And then for the second dice, you'd have to branch out and then branch out. And you can imagine how big that tree diagram would be if every dice has 6 options going from it. So it's great that we have these new tools. Let's do another example. So if you recall the TV show Numbers, maybe you recall it, maybe you don't, but it was a show where a police department has some mathematicians that help consult them and to help them solve crimes. In this one episode, they had a guy claiming to be psychic, and they tried to get him. They just took a deck of cards, said, if you're psychic, pick the correct color of a card 25 times in a row. So what happened was the first few were incorrect, and they all snickered at the psychic, but it actually turned out that he picked all 25 incorrect. It was kind of an interesting thing, because that's actually pretty rare. And so we can answer questions like these very quickly. The probability of getting 25 of these colors wrong, and remember, on a deck of cards, you have red cards and you have black cards. So the probability of getting one of the cards colors wrong is a half, and to get the second card, the probability of getting it wrong is a half, and we have to do that 25 times, which would be quite a lot to write out. So of course, it is in our best interest to maybe get used to using exponents in a case like this. So 1 over 2 to the power of 25. That is a very, very small decimal. I'm going to leave that as a fraction. It works out to 1 over 33,554,432. So, only 1 in about 34 million times would somebody just get them all wrong purely by chance. So another fairly straightforward application of this idea of compound events, but as you can see, we're doing much more complicated problems. Now, the 3 examples we just looked at, all these events were independent. For example, the psychic trying to guess the color of one card, that doesn't affect his chance of identifying the color on the next card. So red or white. It's much like flipping a coin. It's just heads or tails all the time, no matter what. We're going to now do some problems where the events are dependent. Dependent events occur when one event influences the probability of another. So, for example, if you draw a card and don't replace it, that affects the probabilities of drawing a second card, right? So, for example, the probability of, let's say, drawing the ace of diamonds, from a standard deck of 52, that's one specific card. That's 1 out of 52. But let's say, you draw that card, you draw a card, it's not the ace of diamonds, and you draw again, but you don't replace it. So there's no replacement. On the second draw, the probability of getting the ace of diamonds would now be 1 out of 51 because you've got one less card. So if you're not replacing things in a deck of cards, that can lead to the events being dependent, and there's lots of other examples of that. So let's do a few. The math is very similar. We use the multiplicative principle, but we use a little bit different notation for when the events are dependent. So that product rule, multiplying probabilities, we tweak a little bit. The probabilities of A and B, it's still the probability of A times the probability of B, but it's the probability of this notation means the probability of B given that A already happened. Given A already happened. This is sometimes referred to as conditional probability because there's the condition that A has already happened. Conditional probability. It's going to be your job in any given problem to identify whether the probabilities are dependent or independent of each other. Let's do a couple of simple examples, get you used to that idea. So in this question, we have a jar contains only 6 marbles. There's 3 red, 1 blue, 1 green, and 1 yellow. So we're choosing 2 marbles. We're choosing them without replacement. So we choose the first, and then we choose the second. Let's find the probability of picking a yellow marble first, and then a blue marble. So we would write it this way. Probability of getting a yellow and a blue is equal to the probability of using our multiplicative principle, the probability of getting a yellow marble, times the probability of getting a blue marble. But these are dependent events because we're not replacing the marbles. In the second draw, there's only 5 marbles. So it's probability of getting a blue given that a Y has been drawn already. If there is only 1 yellow, then that first probability is 1 out of 6. And given that we've taken 1 yellow, there is 1 blue marble left of the 5 marbles left in the draw in the jar, and that gives us a 1 in 30 chance of getting a yellow, then a blue marble. So look for those keywords. Without replacement, you're looking at dependent events. If you do have replacement, the events would be independent. Let's try this one. Maybe you want to pause the video and try this one on your own first, actually. The probability of drawing 3 face cards in a row from a deck of 52 if the cards are not replaced. If you want to pause and give this a try, please do. If not, just follow along. So let's dive in. The probability of getting 3 face cards, I'll just write 3FC for short for that. So if you need to pull out your diagram of the deck of cards, we've looked at that in several spots already this course, but we have talked about there are 12 face cards of the 52 in a deck. So the chance of getting your first face card is 12 out of 52. But if you're not replacing the cards, for your next draw, there's only 51 cards. And we have taken out 1 of the face cards. There is now only 11 face cards left. And for the third draw, you now only have 50 cards in total left, and we've taken out 2 face cards. There's only 10 left altogether. And all that's left for us to do is multiply these probabilities together. If you multiply the tops, you get 1,320. If you multiply the bottoms, you get 132,600. So I feel like this is a good spot just to remind you guys that there are many ways to express a probability. I would consider this correct. However, that's not easy to kind of interpret and think about. You could put that in lowest terms. In lowest terms, that is 11 over 1,105. That still may be a little hard to look at. You could make that a decimal by dividing. As a decimal, that is 0.00995 to a lot of decimal places, which is, I'll put an approximately equal to here, which is, as a percentage, if you multiply that by 100, it's very close to 1%. It's 0.995%. So basically like a 1 in 100 chance of that happening, 3 face cards in a row. But yes, I would, unless I ask, fraction is okay, percentage is okay, decimal is okay. All right, let's move on. Sometimes tree diagrams can help do more complex problems, and we will do some applications in the next couple of days where a tree diagram will really help us out. So my friend, Mr. LeBlanc, he is a avid cyclist. And in this hypothetical question, let's say that the Weather Channel is forecasting a 30% chance of rain tomorrow. So when the weather's nice, Mr. LeBlanc rides 90% of the time. And just because it rains doesn't mean he's not going to bike, but if it's rainy, he'll only ride his bike 10% of the time. So having that information that there's a 30% chance of rain tomorrow, we want to find the probability that he's going to ride his bike. So we're going to draw a tree diagram to visualize this problem. So I'm going to start it this way. I'm going to do mine off to the left here. So for the first kind of layer of our tree diagram, it can be rainy or it can be sunny. And just below, I'm going to add the probabilities of these things happening as a decimal this time. You'll see why in a second. So 30% is equivalent to 0.3 as a decimal, and that means, this didn't say this in the question, but if there's a 30% chance of rain, then there must be a 70% chance that it'll be sunny, or at least not rainy. And then from there, we can branch it off. So if it rains, Mr. LeBlanc can ride or not ride. So I'm just going to use a check mark for the case he does ride, and I'll put an X if he doesn't. And in our next one, put a check mark, he can ride or he cannot ride. And now we have to, if we go back to the wording of the question, if it rains, Mr. LeBlanc is going to ride his bike only 10% of the time. That means if it rains, he will not be riding it 90% of the time. When the weather is nice, he rides his bike 90% of the time. And that means that when the weather is nice, he will not ride his bike 10% of the time. And so we've got a tree diagram showing all the possible options: rainy and riding, rainy not riding, sunny and riding, sunny and not riding. And we can find the probability of each branch by using our new knowledge and multiplying those decimals together. So let's finish our question. What's the probability that Mr. LeBlanc goes for a ride? Well, that's equal to, let me just erase that plus sign. So that is equal to, there's two cases, right? So this goes back to yesterday. It could rain and ride, or it could be sunny and he rides. And those two things can't both happen at the same time. It can't be rainy and sunny. So we're going to add those two things together. So we're going to find the probability that it rains and he rides, and we'll add the probability that it's sunny and he rides. And we'll use today's knowledge to do that. The probability that it's rains and he rides is 0.3 times 0.1. And the probability of it being sunny and he rides would be 0.7 times 0.9. And And you can work this out. You get 0.03 plus 0.63, 0.66. So that is a 66% chance of riding, that Mr. LeBlanc will ride his bike tomorrow. So a tree diagram can help visualize some more complex problems. We're going to finish off today's lesson with the application of compound events I call the birthday problem. So in one of your participation activities for attendance, I asked you guys to put your birthday down on a Jamboard with a little sticky. So our online class has, the attendance is still fluctuating, but around 32 students. Maybe 20 to 25 of you guys actually are regularly participating at this point. So I haven't seen the results yet, but only with 6 people putting their birthdays up, we hadn't had a match yet. But it's really interesting to think, of this big group we have, what's the likelihood that 2 of us share a birthday? Well, we can figure it out now with the knowledge we have. So to start off, a really simple problem. When I say in this room, let's assume that there's about 20 active people, including me, just to keep things easy. So the probability that a person in this room chosen at random would share your birthday. So the probability of having a shared birthday, pretty easy to find out. They have to match your birthday. So my birthday is December 29th. If I randomly picked one of you guys and find the probability of your birthday being the same as mine, there's only one day that matches my birthday out of the 365 days in a year. We'll ignore the leap year with February 29th. So the probability for one person matching your birthday would be 1 out of 365. It's actually sometimes easier to calculate, and you'll see this later for when you add more and more people, but the probability that a random person would not share your birthday would be, so I'll say that no shared birthday. So this is the complement of that first event. It would be 364 out of 365. And for the rest of this question, it'll actually be easier for us to think about the probability that nobody would share a birthday. So let me show you why. In part C, so we're going to do this birthday problem for just a group of 4 people. We're going to determine the probability that no one in this group of 4 people shares a birthday. So we're going to find the probability of no shared birthday. I'll just say B day for short. So with these 4 people, we have to think about, if we were to ask these people one at a time for their birthday, the first person's birthday doesn't matter, right? If we ask one person, like one person is going to have a birthday, and that's just one day, so it doesn't affect anything else. It's only when we get to the second and third and fourth that we have to worry about not matching that birthday. So the first person has basically 365 out of the 365 days to choose from. That's person 1. The next person, though, the second person, well, they can't match the first person. They only have 364 possible days to choose from. The third person can't match the previous 2. They only have 363 days to choose from. And the last person only has 362 days to choose from. And so you can see how that first person doesn't matter, because that just divides to 1. But this is how you could set this problem up. And now you can actually calculate the probability of having no shared birthday. So if you want to do that at home quickly, you can do that too, just to verify what I get here. So I'm going to keep this to 4 decimal places, 0.9836, which is equal to, as a percentage, 98.36%. So like, I think that most of us, that makes sense. 4 people, there's a lot of days in a year. It should be a pretty high chance that nobody shares a birthday. So let's extend this idea to kind of like our group with maybe about 20 people. So it's going to be the same idea. No shared B-Day. So the first person is going to have all 365 days out of 365 days to choose from. The second person, has to be a different birthday, only has 364. And then the third person has 363. And we have to do this for all 20 people. So if you go all the way down the line, the probability for the last person will be on the bottom. They'll have out of the 365 days. But on the top, we have to figure out how many days are left for them to choose from. And so if you count down from 365 and count down 20 times, you're going to be left with 346. There are 20 numbers, including 346 and 365 there. So if you can calculate this, this is going to give you the probability that nobody shares a birthday in a group of about 20 people. So if you want to take a second to try that, I'll do it too. So you can pause it and try it, or you can just like take my word for it. What's interesting is later on in the course, we'll actually learn some easier ways to do this kind of calculation. All right, so I did it at home. So I got 0.588 to 4 decimal 0.5886, which as a percentage of 58.86% chance of 2 people sharing a of nobody sharing a birthday in a group of 20. Now that's actually, it's getting kind of low. If we move to part E and we think about complements, well, either nobody shares a birthday or at least 2 people share a birthday and maybe more, right? So for part E, using our answer in D, the probability that 2 people have a birthday in common probability that 2 people share a birthday, using our formula for events that are complements from a few days ago, that would be equal to 1 minus the probability of having no shared birthday, which we just calculated. So that would be 1 minus 0.5886, and that's 0.4114 about. So 41.14%. So that's really interesting that even in a group of 20 people, you're over 41% likely that 2 people share the same birthday. So it'll be interesting to see if that works out for us. The probabilities get even crazier with the more people you add. For example, if you had 30 people in a classroom, the chance of 2 people sharing a birthday with just 30 people, it's about 71%. So you're definitely more likely than not in a group of 30 people. I believe it gets around 50 people. You're talking, well, I can just do it quickly actually. With 50 people, with 50 people, you're pushing 90%, even higher. So the birthday problem is a really interesting application of what we've done today. So for your next steps, so as usual, I won't do this all the time, but I've made a little formative quiz, just seeing if you can pick off whether events are dependent or independent or not. And I've posted a PDF with some questions that you can try out. In our next couple of lessons, we'll be applying these probability concepts to a couple areas you may be interested in. One, we're going to apply this to sports and the probability of a team winning a playoff series, whether it's out of 5 games or out of 7 games. And we'll also look at medical tests and false positives and false negatives, and talk about how worried you should be if you actually test positive for a disease. That should be really interesting. I'm looking forward to it.